look at the math associated with both finding enthalpy of vaporization as well as looking at the heating and cooling curves. So the first thing we're going to look at is our vapor pressure equation. This is called the Clausius Clapeyron equation, and this relates our vapor pressure, indicated by the capital P's, to our temperature, indicated by the capital T's. Alright, so if we look at this equation, we have the natural log of the ratio of two pressures, so pressure 1 and pressure 2, is equal to negative delta H of vaporization, so enthalpy of vaporization value, which if you remember is the constant value for a substance, divided by R, our gas constant, and in this case we're looking at energy units because enthalpy of vaporization is energy. So down here we have the value given for R. So this is what we're going to use. And notice the units. So this is joules. So when we go to use this in our equation, we want to keep in mind the units. Alright, then for our equation, times 1 over our temperature with a subscript of 2, which relates to our pressure with a subscript of 2, minus 1 over T1, which relates to our P1. Alright, so for this equation, the units of our pressure can be anything as long as they're the same. So atmospheres, millimeters of mercury, torr, doesn't matter. The units of temperature must be in Kelvin. Alright, so if we have Celsius, we have to convert. And then our units of R must match our units for our delta H in terms of joules or kilojoules. Alright, so we're going to do an example with this equation. Alright, so here's our example. The vapor pressure of water, 17.54 torr at 20 degrees Celsius. What is the vapor pressure of water at 35 degrees Celsius? Alright, so in this case we are given a pressure and a temperature, and we're asked for pressure at a different temperature. We're also given the delta H for vaporization of water down here. So this is our constant value for water. And of course we know our R value. Okay, we've already looked at that. R is going to be 8.314 joules per mole Kelvin. Alright, so now let's look at what we need to do to solve this then. Let's fill in values for our equation. So we have the ln. We're going to assign our pressure values. Now we're given one pressure and we're trying to solve the second. So I like to put my variable on the top as P2. You don't have to do this. You can assign it as P1. It's completely up to you. But I think it's easier seeing a variable on the top than the bottom. So I'm going to put the 17.54 as my P1 on the bottom of the fraction. Alright, then equals my delta H value, so negative 40.7. And notice this is kilojoules. Alright, so that means that I want my R value to also be kilojoules. So we're going to move the decimal place over 3 places. So 0.008314 is our value for R. Alright, then times 1 over. Now we have T2, which has to relate to P2. So we're going to look at the temperature associated with P2, and P2 is our variable. So our temperature associated with it is 35 degrees Celsius. Alright, so that means we need to convert our 35 degrees Celsius into our Kelvin. So we're going to add 273. So this becomes 308. Alright, then minus 1 over our P1 was 20 degrees Celsius, so that becomes 293. Alright, so there's our equation that we've set up. Now we want to look at solving this. Alright, so to solve this, our variable is over here, so everything on the right side of the equal sign is a real number, so we can put this into our equation, into our calculator to solve it. So I'm going to keep the left side the same for now. And I'm going to fill in what this is in my calculator. Alright, so let's look at what we have. So we have 40.7. See if I can get this on here. 40.7 divided by 0.008314. So I'm just doing that first part. So 4,895.36. And I brought down the negative sign. Alright, then we'll do the second part. So 1 divided by 308, and notice I'm using parentheses. Make sure that you use parentheses when you're putting in multiple functions at the same time. Your calculator is not smart. You need to be smarter. Alright, so 0.000166, and it has a negative. Alright, so I've got those two parts of my equation, then I'm going to multiply them together. And the negatives will cancel out and go away. So now I have ln of P2 over 17.54 is equal to 0.8137. Alright, from multiplying those two together. And now, how do we get rid of natural log? We have to use base E. So if you look on your calculator, on mine I have an ln button here, and above it is my base E. So if I do second ln, it gives me the base E. Then I'm doing my value, 0.8157. And I get 2.26, oops, 0.8137, let's try that again. Alright, 2.256. Alright, the ln is going to go away, so now I have P2 over 17.54 is equal to E raised to the 0.8137, which is 2.256. Alright, so now I can just multiply the 17.54 over here to solve for my P2. $39.6. And the units are going to be the same pressure units we had before, which in this case is torr. Alright, so increasing our temperature from 20 degrees Celsius to 35 degrees Celsius also increases our pressure. Alright, one other thing we want to look at with the Clausius Clapeyron equation is how we can use this in a graph. Alright, if we look at the Clausius Clapeyron equation, it's actually the equation of a straight line. Alright, so I'm going to write it out again so you can see. ln of our P2 over P1 is equal to negative delta H over R times 1 over T2 minus 1 over T1. Alright, so this is our Clausius Clapeyron equation. This is the equation of a straight line. The ln of our pressure ratio is going to be our y. Our 1 over temperature is going to be our x. And our delta H over R is going to be the m. Alright, so if we look at it in this manner, we can see that if we graph our pressures by our 1 over temperature, we should be able to get a straight line correlation with our data, and it allows us to calculate what delta H should be. So notice up here, the slope of my line should be negative delta H divided by R. Okay, up here it has delta H divided by N times R, indicating it needs to be a mole ratio. Alright, but if we know we're already working with delta H, then we don't have to worry about that. The N is 1. Alright, so that means if I have a graph and I'm trying to find delta H of vaporization for a substance, I just need to look at the slope of the line to calculate delta H. Alright, so here's my slope given by my equation. So my slope is going to be negative 4,576, can't read, 0.5, and that's going to equal negative delta H over R. Alright, so we just have to fill in our R value, which we already know. So if I fill in R, and I'm going to use the 8.314, this just means my delta H will then be in joules. Alright, multiplying R over here, the negatives are going to cancel out. Alright, so I have 4,576.5 times 8.314, 38,049, and remember this is joules because our R was joules. This could also be written as 38.0 kilojoules. Alright, so this would be my delta H of vaporization for whatever this substance is. Alright, we'll stop there for this video. This is talking about the Clausius Clapeyron equation and vaporization. And then next time we will look at heating and cooling curves. Thank you.